So we're now ready to introduce this brilliant idea of Ando Nika back in the early 1990s on what we now know as the Nika covariance condition. Okay, so it's really just simple idea by start by observing what happens when you consider the lab regular representation. So we know each of these lambda p is going to be isometry. But what is range projection? So lambda p star, if you consider it on a basic vector, so let's say you consider it on EQ, what happens is that if your Q is inside PP, okay, so in other words, if your Q can be starting from P, then the lambda P star will cancel out that P, and then you put the lambda P, you put the P back, so you get EQ as well. But if your Q is not inside PP, then clearly this EQ will be orthogonal to all of the range of lambda P. So it's not going to be inside the range. So this range projection will return a zero. Okay, so that's a zero. So in other words, your lambda p star is very easy to describe. Okay, so this is just the projection onto the span, say the span closure of all the EQ where Q is inside PP. Okay, so the principal right ideal of this little p. All right, so this is you have an orthonormal basis for this range projection. Okay, you described it very easily. And now if you think about what happens, because you have a quasi-lattice order, so let's say P is quasi-lattice ordered. So if you take two of them, okay, let's say PP star times lambda Q star, okay, you take two of them. So this is the product of two projections, okay? And well, they're just, each projection is basically spanned by a lot of these basic orthonormal vectors. And when you take the product, it's basically projection onto their intersection, which is spanned by the intersection of these orthonormal vectors. So this is basically the projection onto the span closure of all the, let's not use Q anymore, let's say EX, where X is, well, it has to be inside the range of P, and it's also inside the range of Q, okay? And there are just really two cases from there, okay? You realize, well, this is the intersection of the two principal right ideal, and we see the quasi-lattice order just means this intersection is either empty or is equal to another principal right ideal where for some R, for some least common upper bound, okay? So in other words, if you take the range projection of P and Q, then you either get a zero if the P and Q has no common upper bound, okay, so sometimes we write it as an infinity, in other words, no common upper bound, or you get some another range projection, okay, if you say P and Q, if this, as long as it's non-empty, then quasi-lattice order tells you this has the least upper bound. So in other words, your PP intersect QP is going to be equal to RP, okay? R is your least upper bound. Then your range projection, the multiplication is the range projection of the lambda R, okay? You get another range projection. And this condition is now captured by a commuting isometry, okay? If you just take, for example, if you take your semigroup to be n squared, then this condition is not captured by the any two commuting isometry. Okay, if you have any two commuting isometry, the range projection may not even commute actually. Okay, so here, as you can see, if you change the position of P and Q, do lambda Q star, lambda P star, then apparently that's still equals to lambda R squared. Okay, lambda R star. So in any case, so that looks like a condition that's missing inside the old definition of the universal semigroup C-star algebra, and that's basically motivate Nika's definition. So here's the definition. So we say an isometric representation, let's say V from P to some B of H is Nika covariant. So this is kind of a standard notation right now. Okay, back then in his old paper, of course, Nika only called it covariant representations, but now we all call it Nika covariant. Right, but anyways, basically you just write the same thing for the what happens to the left regular. Okay, so for every P and Q inside your P, if you consider the range projection VP and VP star, and you do VQ and VQ star, that's two things. So if P and Q has a upper bound, so it has the least upper bound by the quasi-lattice order, then you get the VR and VR star. And if otherwise, if you P and Q has no upper bound, then these two range projections, they're actually orthogonal to each other. Okay. So let me give you a quick example on we saw that n squared is a quasi-lattice order, actually all the nkr. But let's see what happens. What's the missing condition from compared to the commuting isometry? So if you consider on the n squared, if you just take p to be 1, 0, and if you take q is equal to 0, 1, well, of course, PQ, they have a least upper bound that's just equal to 1, 1, okay? So it's just their sum. So in other words, if you want to have a Nika covariant, that just implies if you take P, which corresponds to, say, V1, and Q corresponds to V2, that should be equals to the V of 1, 1, okay, which is just the product of V1, V2, okay, times adjoint, okay, V1, V2 adjoint. And because V1, V2, again, they're still a representation of n squared, so they still commute. So I can write as V2, V1, so the V2 is on the right side. So this is just V1, V2, and then I have a V1 star, I have a V2 star. And because isometries, you can cancel out, you can multiply, say, V1 star on the left and cancel out the V1. Okay, so V1, V1, well, you cannot cancel out the star on the right, but you can use the star on the left to cancel out the V1 on the left. So you multiply V1 star on the left. Okay, so you have V2, V2 star, and then you multiply V2 on the right. This is going to be equals to V1 star V1, and then you have a V2 V1 star, you have V2 star V2, and things are cancel out, and these two cancel out. So what you have is that V1 star V2 is equals to V2 V1 star. So in other words, this condition is basically saying V1 and V2, they not only they commute, but they also commute with the adjoint of each other. Okay, so sometimes this is called a star commute, or sometimes if they commute and if they star commute, this is also called the doubly commute. Doubly commute. Okay, doubly commute. All right, so if this V1, V2 are Nika covariant, then they have to satisfy this condition, and the converse is actually also true. If you have a doubly commuting isometries, then it'll give you a Nika covariant representation of the n squared. So that's really the missing condition. And in fact, even in terms of wall decomposition, these doubly commuting isometries, their wall decomposition is much nicer. Okay, this is observed long before Nika, the result of Slusinski actually, show that they have a nice wall decomposition, basically decompose as unitary and unitary, unitary shift, shift unitary, and then the last piece is bi-shift, okay, basically a left regular piece. And that's just shows that this is just basically capture what's missing in terms of this universal one. Let me just give one more example because this is, we're going back to this later on. This is kind of important. So if you take the free semigroup, let's say it's generated by E1 up to EK, and for every I not equal to j, you see that EI with EJ, they have no common upper bound. Okay, so sometimes we write it as infinity. And if your representation is just determined by this, if you let VI to be V of these EI, this VI will determine a representation of this free semigroup. And what is Nika covariant condition tells you is that because EI, EJ, they have no common upper bound, so their projection, their range projection has to be equal to 0. Okay, in other words, this VI star is a collection of pairwise orthogonal projections. Okay, so when you have a class of pairwise orthogonal projections, there's an equivalent definition. So equivalently, This is just means that if you take the sum of these vi star, well, you know they're orthogonal to each other. So when you take the sum of a bunch of orthogonal projections, they cannot exceed the identity. So that's less than equal to identity. Okay, I go from 1 to k. And in fact, they are actually equivalent. Okay, so if you assume they satisfy, if you take their sum of their range projection less than equal to identity, then you get a Nika covariant representation and vice versa. Okay, so this is sometimes called the row isometry condition. Okay, so the idea is you take a row vector v1 up to vk, then you think about it as a operator from k copies of h to h, and that's going to be an isometry, and that's exactly what it means. Okay, so sometimes called the row isometry. And if you taken pure math 810, for example, you probably realize some C-star algebra arising from this relation. So if I replace this inequality by equality, if I take sum of k isometry, the range projection, if they're equals to the identity, then there's a very well-known C-star algebra that says their C-star algebra, they're always isomorphic to each other. This is the called the Kunz C-star algebra, the O of k. Okay, so that's where you see this. Even if you view the C-star algebra this way, it's related to these kind of representation relates to a lot of very well-known C-star algebra. Okay.